The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI Web Sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next presenter is Oscar Antommattei, and he has lots of results from field on this topic. He will talk about dealing with plastic settlement cracking, case studies, and lessons learned.
Good morning, everyone. I'm going to promise you something. I have no equation and no figure there, okay? And maybe the amount of writing that I have there can be counted, so you should be good. So, interestingly, I'm talking here to this committee meeting as part of one of the committee members, but I brought a bunch of questions, as part of one of the session discussions we were having, and I think we eventually decided to come up with these, and I think it has been great. The two presentations before has been great. I know the next one is awesome, so I'll try to do my best. And obviously, the question is, how will you use all this information in the industry? That's going to be my perspective. It's important that you guys, especially the ones that are in research and developing in your careers, understand all of the things that you do are going to end up in practice. And either it's going to affect positively or negatively, so you need to be very careful what you say. So with that being said, for those of you that don't understand where I'm coming from, I come from doing a lot of design build projects. My concentration on the discussion is going to be now into more of a 100-year life type of projects. Now think about this, the project's 100-year service life are not going to be dealing with the same mixes that you're going to see in the urban or rural type of neighborhoods, right? You're going to be dealing with a lot of different properties and a lot of different challenges that are not the same. So I'm trying to put a position about something just because there's a couple of tests here and there, even hundreds of tests in local areas, and then extrapolate that to 50 states, I believe is wrong. So that's the way that I'm looking at things right now. So I'm going to talk a little bit about an introduction, which I already started doing a little bit of that. And then fundamentals, very basic. I'm not going to go into the whole theories that like you saw already. So now you're experts already. And then lessons, a few case studies, something that is going to show you different actual settlement cracks and how they show different attributes, different materials, different sections, different conditions. In my opinion, what we learned from that experience, and then some closing remarks in my view of how we should be moving forward and what we should be doing with this information. So talking about, my point of view, these are some recent projects, and all of these, as you can see, they're pretty much monumental bridges. And we're talking these 3 bridges in the area of New York. All of them are 3 different construction schemes, different JVs, different concepts, but they had the same durability requirements for service life. 100 years, 125 years. So now you start thinking about, okay, so what type of concrete you're dealing with there. I'll tell you, typically the concrete is going to be ternary mixes. There's going to be low water cement ratios, not, pretty much from 0.32 to 0.4, depending the application. And the amount of rebar, it's a little bit crazy. The type of rebar changes, right? You use a lot of stainless steel. And then they also, there's consideration into the cracking, the maintenance, how you're going to repair things. So that's very important to consider once you're thinking about then how do you determine what settlement cracking means to the industry and how you're going to address it, right? This project is a more recent one. This one is also 100-year service life. Interestingly, here we had already a DOT that was very focused on slumps, and they have been participating a lot in these seminars about the studies on cracking in bridge decks, and they were just tied up with the slump. Now you start thinking about how you're going to use low water cement ratio that needs to meet freezing and thaw requirements, scaling requirements, shrinkage requirements, permeability requirements, and strength requirements, and then you need to pump it, and then keep that slump below 4 inches, okay? And the thing is, interestingly here, they have stainless steel all across the board, and then we're going to come with a chip seal and cover the whole surface. So you start thinking, okay, then what is my risk? But that was part of the problem. And here what we ended up doing was, instead of pumping the entire bridge, we ended up conveying the entire bridge. So we had to set up conveyor belts and place it by conveying methods, which is unheard of, but was the way that we handle. Another thing to consider is that not all concretes are made equal. So when research, people go to a bridge that is next door, and they may be in the McDonald's looking at the bridge, and they know that it's easy to pump with 4 inches. Not all the concretes are made equal. So you can see how, extrapolating or even having a statement that is going to cover all bridge decks in the United States and thinking about slump, it doesn't make sense for all the bridges, right? So these are some of the bridges, some of the conditions that you have to do sometimes, right? You have to sometimes barge your concrete, you have to pump, and there's another photo I couldn't put, but it's pretty much pumping vertically too. And that's the way that you build some of your bridge decks when you are in the middle of the river. Also, even though this doesn't show up in many ACI documents or many people don't realize it, that's how we build work today. That is the way we build work today. If you can see through, you're not doing it right? So that's pretty much your check method, right? Your designers put as much rebar as you can so you cannot see through. If you see through, there's a problem, right? So think about now, you're going to have to build and consolidate all your maximum 3.5, 4-inch concrete with a water cement ratio of 0.35, silica fume, and all of those good things that you know. And maybe they also put there that you need to use 1.5 inch aggregate, right? Which is already a challenge. We have seen that. So think about constructability, right? It is a little bit of a challenge, but hey, the contractor has the money, right? And then this is a lot of the things that start to happen then when you think about, okay, we were able to decide that the concrete was going to be placeable, but hey, your paver can do it all. You don't overfinish that with your hand finishing because you're going to be bringing paste to the top, and your mix, you should be able to figure it out with your concrete producer. Technologies today, hey, we have so many mixers. Figure it out. That's what's happening. But hey, from the lab, looking at how things work in the lab, it's easy. That's concrete for a 100-year service life project. That's how it comes out of the paper, right? That's low water cement, 100-year service life concrete. That's a challenge, right? If you don't cause dispersion to allow that to be finished properly, it is really difficult to finish. But again, I think you guys understand where I'm heading. Some of the fundamentals have you guys already, I think learned more than you're going to learn from mine, but let me put some figures here and not bring any equations. The basics, right? You have obviously a very restrictive element near the surface, right? And you have your concrete to some extent settling and bleeding at the same time. Many concrete today doesn't even bleed, but hey, let's call it that there's settlement. And there's eventually a condition that turns out to break that concrete at the top, right? Some cases you can see the void here. Some cases you don't see any void and you just see the top crack. And when you look at it from the top and from the top, you can see depending on where your obstructions are near the surface, you can see the different cracks that forms. And then here you can see the same thing where you can see the crack at the top. But the thing that I want to also mention is that when people is doing research and people is trying to think and communicate that there's a potential for sediment cracking, I believe there's two things that need to be verified. Is there a crack connected to the obstruction? So there needs to be a reason to take a core. And what is the undulation happening at the top? So there can be a confirmation that there's true settlement cracking happening and not other mechanisms happening, right? And not trying to extrapolate just because there's transverse rebar and you have a crack that is transverse, that's a settlement crack. That's a flaw in the research. The other thing is understanding the cross-section, right? Where your cross-section is, because you may not have there a reason to have a rebar obstruction, but their cross-section changes can also cause you a settlement crack. So those are some of the basics, right? If you look at ACI, you can see settlement cracks in bridge deck can be reduced by increasing the concrete cover along with the mixture that minimizes bleeding and settlement. So obviously you're trying to make sure that you have the rebar that is not too close to the surface, and obviously that your mix is not prone to settlement, right? And then there's some comments about use of slump concrete is also recommended to help prevent settlement cracks in bridge decks. And that's where we need to be a little bit more subjective and smart about how it is approached and where that's applicable and where it's not applicable. If you go back to the 1975 work, which is used as reference, interestingly, still today, you see this being the main reference that is used to talk about settlement cracking fundamentals. You go to research that is done today, okay, talking about almost 40 years ago. And we still are talking that this is the main research that governs a lot of the discussions today. Even though the whole chemistry and different mixes that we're seeing today may completely affect how we explain settlement cracking today. But in concepts, there was observations that found that increasing slump, is likely, increase the percent of the slabs crack, right? And the same with the more larger bar size, you also saw that. But then interestingly here, the cover has a very predominant effect, right? And this is the interesting part, because some of the reasons why we're here today is because when we were talking about settlement cracking in our committee meeting, one of the elements that was not identifying the cause of cracking was the design, right? And it was clearly talked that the producer and the contractor is pretty much controlling the effects of settlement cracks. And I automatically had to stand up and kind of try to make the correction, because the structural designers are part of the problem for settlement cracking. In addition to that, when you go to build a bridge, if you have built a bridge, what a structural engineer tells you is that they don't want the concrete to settle to set too fast. So if you have a 4-hour pour, they tell you they want the entire 4-hour pour of concrete to try to set at the same time. What does that mean? You end up over retarding the concrete that you're using in your bridge deck to help the structural engineer feel more comfortable about how the stresses are going to be transferred in the bridge once the concrete hardens. But again, research studies keep blaming the producer and the contractor on settlement cracking. And then we have more recent studies by Darwin, and Darwin talks about the impacts from slump to settlement cracking, and then have some of the inputs on the amount of cementitious material. The water-cement ratio you see here, which is obviously not representative of 100-year service life projects, neither these numbers. And then the slumps that are really low, that are causing some trouble in the industry. And then these numbers are also something that you would not see in a 100-year service life project. Just because of the water-cement ratio you need and the properties that you need for scaling permeability, keep adding, all the other things, you end up pretty much, even though you have a 5,000 PSI requirement, your concrete end up being an 8,000, 9,000 PSI, just because of the other properties, okay? But you're going to hear more about this research later. One of you guys are going to talk about that research, so it's going to be interesting to hear about that. So now case studies. I'll just show you examples. Again, no equations. Just need to keep an eye on the pictures. And I put a dot here on the rebar just to make sure that you guys could see the rebar was there. The photo was not very clear on the rebar, but you could see now where the rebar location was. So this was, after doing about 60 different placements of the same concrete with the same type of element. We had one time in the winter, one of the crews that did not forecast it very well the weather. They did not forecast very well the weather. They didn't provide enough cold weather protection. So we ended up having a delayed set in that concrete. Pretty much the concrete temperature was too low. The concrete never pretty much got hard until after more than 24 or 48 hours. But this is a SCC mix, very low water-cement ratio, silica film concrete, high strength, has never had any problem with cracking on the deck. And then we saw that day, the whole delay, set time delay, caused problems. So then we had to cut sections. We had to remove the whole deck and pretty much, spend about $3 million replacing the deck. But once we cut that, just to learn where the cracking was coming from, we saw cracking coming from the top rebar, which then obviously you start making sense. You don't need to go too much into the scientific theories. But obviously you start thinking about, well, longer set times. You know, the concrete didn't set, it was plastic. Then obviously you have that restriction on top. So you can see the crack pretty nicely how it shows up from the top of the deck, from the top of the rebar. Then obviously you keep looking, and then you keep seeing that, well, you know, where is that crack coming from? Because there's no restriction there. So that also shows up in the, and you can see the other ones coming directly from the top of the rebar. This one actually didn't go all the way through, but you see the restriction and you see the connection, even though it doesn't touches the rebar. And here you see the same effects. You see the crack, go to the rebar, crack, going to the rebar, crack, going to nowhere. And then here there's like, seems to be a crack starting to form there, but it doesn't connect all the way down to the rebar. But again, you start looking at the project never had an issue with cracking on these decks. And then the day that you allow the material to set too long, unexpectedly, then you end up with this issue. So you learn a little bit about what happened with those cracks. This is a thin element, not a thick element, high performance SCC concrete. This one is completely different. Now you get to Canada, and we were doing some work there with thick elements, some mass mat placements, mass foundations, and now you're talking about low slump. Slump cannot exceed the 4 inches, so actually you're dealing pretty much with 3-inch slumps in average. And the mix obviously is lower heat. You have, you know, a large aggregate. You have less cement tissues. Your water cement ratio is above 0.4, so it's not necessarily the low water cement ratio you typically see in 100-year service life. So this is more of a typical mass placement. Now in this case, we were also in the winter time, and you know the amount of retarded was not adjusted for winter. So we ended up again with a longer set time, thicker section. We get a phone call eventually during, you know, a few days after the placement. And then you can pretty much see, and hopefully you can see it there, but you can see there the crack, you can see 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 the crack, right? So for the rebars, right? And here you have a little more close-ups. But interestingly here, what you can see also, as you see the reflection of the light, is the undulation a little bit. You can see an undulation. So this is kind of plastic settlement by the book, okay? And now we're talking 3.5-inch slump concrete, okay? Still show the issue. Again, longer set times, cold weather, you know, additional set retarding materials in the mix. Here you have a close-up of that concrete. You can see the concrete where it cracked pretty much. And you even can see a little bit of here, if you look at the ray of light and the whole thing, you can see a little bit of that undulation too. Now here is where we get and you find, and this is a case, I always like to talk about where there's a problem when there's no problems, okay? So now we're talking, okay, so we have a large mat placement that we know thicker elements have a problem. We know that if you have, you know, the low cementitious materials and high water cement ratios, you might end up with a problem. So here is an issue, a condition that we didn't have any cracking, okay? And this is more recent work. This is a little more high-performance concrete from a perspective of mass, reducing thermal, and also strength. So these are over 6,000 PSI concrete for mass placement with high-volume replacements. It had extended workability, a little bit of set retarding, but not enough to overly retard. And we completed this placement with about 7 to 8-inch slump concrete, okay? So now we're dealing with high slump. So now if I look at my picture here, we say, whoops, if I went to 3.5 inches and I got all this problem, I don't want to even think what happened here if I go to 7-inch slump or 8-inch slump concrete. Now what is different? My water cement ratio here is about 0.38 because I have a high volume replacement of SEMs to get low heat. So then I have a more viscous material, right? And obviously you see no cracking. Beautiful concrete. This is not actually SCC, 7-8-inch slump concrete, internally vibrated with high SEMs. So now the interesting one, this one I wanted to leave it for the end. This one was just an oops, okay? So this is just a case of settlement cracking that doesn't happen over the rebar. You see what I put at the top? There's a snow melt system over the entire slab, and they put it on top of the top rebar. So you can see how pretty cool, you can see how it curves, the snow melt. So you see the snow melt system pretty much. And this mix was a 20% fly ash. It was about 5-inch, 4.5-inch lump. When you look at it from production, I think in actual, the requirements were max 5. So you could see some 3s, some 4s, some 5s. So we're talking about average around 4. And 20% fly ash or 4,500 psi concrete. Not too fancy concrete, but this one just shows another case where the actual design, this is a design that called out for the snow melt on top of the rebar, ended up causing a problem, right? So some of the things that I want to communicate from my lessons learned on this. So based on the case studies I show, plastic settlement cracking should be visible within the first 24-48 hours. So when you're reading research and you're seeing that there's attributions to cracking, well, you know what the first assessment should be? What was the condition after a couple of days of placement? If you see no cracks there, how can you attribute the cracks to a plastic settlement issue? Right? And if you want to verify that, then before you get the cracks, you should drill some cores and see if there's something happening under that concrete. But pretty much what we saw and we learned, when you get settlement cracking, that crack shows up. You're going to see the cracks, it's going to happen, and you're going to see it in a couple of days. Obviously, let the concrete cool down a little bit and get dry, and you will easily be able to find it. Now, the risk of plastic settlement cracking, what we found, increases for concrete having a delay or longer set time, in particularly when you're talking about low temperatures, right? So in our cases, it was low temperature related. Obviously, it has set retarder. But in particular, it was the issue with once you get to that cooler temperature, you didn't adjust your set retarding, it caused problems. Also, the larger, thicker sections showed to be a little bit of a challenge there. I wouldn't say that it's perfectly attributed to that. I think it's something on a case-by-case basis, but seemed to be obviously a condition that we would take an additional set of eyes. And then obviously the embeds closer to that surface, you know. But I cannot find in our experience that the high or low slumps have been a problem. Cannot. I'm sorry. You know, that's what we're doing, and it's mainly because what we do, a lot of it has low water cement ratio. So the reason for just making a statement, a blanket statement, and saying that slump is just the master of controlling plastic settlement cracking, I'm sorry, I have a problem with that. So in my closing remarks, I would say that limitations from research can result in misleading actions when the knowledge is used outside of the research scope. If the research scope was to use 0.45 water cement ratio and you saw something that caused a problem, you know what? The conclusions are related to 0.45 water cement ratio with the materials that you use in your research. They're not extrapolatable to the entire 50 states for any concrete. Knowledge from research can misrepresent the intent of durability performance requirements, in particular to meet constructability of 100-year service life projects. Again, we're talking about bridge decks as one thing. Today, bridges, modern bridges, have 100-year service life with requirements that are making the concrete more difficult to construct. What you build in the middle of your city for your maybe 50 years using local contractors may not be what you do for a monumental bridge that requires 100 years. And just saying that that's applicable is wrong. The potential risk for plastic settlement and slump requirements needs to be evaluated on a case-by-case basis on consideration to the local material properties, mixture proportions, performance requirements, design criteria, and construction demands. Again, we go back, and this is going, I tell you, this goes from the heart to the younger, engineers that are growing and getting into the industry. Don't extrapolate. Be cautious with what you say, because you know what? What the audience in the industry is doing is believing that just because somebody wrote it in a research paper and it was peer reviewed to be right by the information that is there, is right. And that is wrong. Risk of plastic settlement cracking is not limited to one single and simplified variable such as a slump. We need to stop the thing about just saying a slump is a problem. Okay? If there is a need to understand if a slump is a problem with your mix and with your project, then there should be a performance requirement to test that concrete under the conditions that the owner want and see if that actually causes cracking. Extrapolating and making a blanket statement just to make it easy is not good. And then design construction materials and weather conditions will directly affect the risk of plastic settlement cracking. Again, it's not a one single thing. It's not a one-party thing. Contractors do the best they can to build the best they can. But if the design is wrong, the owner is going to get the wrong thing too. So with that, thank you very much, and I hope you guys understand what I'm saying. Thank you.
Oscar, got one question on the, have you seen any, talking a lot about slump and not being a relationship. What about cover over the bars? You mentioned in one of the slides, the closer it is, like the one you had with the high slump and on those foundation members, did you have a deeper cover on those, or?
No, actually, on that one, we didn't see much of a cover thing. I think the example of cover would be more with the snow melt. That it was just, so that example photo would show a little bit more about the discussion of cover.
Yeah.
No, because the other foundations that we did that had the same condition, but it was not overly retarded for temperature and said retarded didn't show any cracking. So I wouldn't say that those deep foundations were a good example of talking about cover. I think the snow melt one that shows that it was so close to the surface and it reflected on top was a big issue. Yeah.
Oscar, nice presentation. You alluded to the specification limitations that you see sometimes. If you had one thing you could change, or maybe two things, or that you would ask spec writers to do to make this issue maybe less of a risk, what would you do?
Well, I think that one of the main things, and I will try to make it global because one or two are kind of limited, but try to understand the construction demands in general. As you try to build your specs and you want to create some prescriptiveness just to be safe, because that's the way that you like to do things, if you're going to prescribe something, try to bring that contractor in early on, work with the concrete producer, understand, okay, what are my construction demands, where do you have challenges, what can the design do to help the construction process be a more effective and constructible way. And then on a case-by-case basis, you may have to decide, hey, maybe the slump is what we want to manage today. Well, maybe, are we really needing that water cement ratio or that strength to be a 28-day strength? That's another thing, right? A lot of the things when you go to private work, instead of public agencies, you can manage understanding the construction demands. You can say, do we need a strength at 28 days? No. Can we push that to 56 days? Okay, now, you can reduce now a lot of the other concerns for durability, given that you're not pushing that 28-day strength, right? So there's a lot of that is going to be on a case-by-case basis, but at the end, bottom line, to understand construction demands. That's the key.
Thank you.
Sure.
Let me ask you a question. When they decide to increase the slump in the field, and we have seen it in many bridge deck placements, what is the more convenient way for the contractor? Let's say they make the concrete, and concrete is in a truck, slump is low. Do they add admixtures or do they add water?
Yeah, typically in high performance concrete, you rarely see an additional water on site. You typically manage the additional water with admixtures. That being said, not all the projects are managed or have the same limitation. And in some cases, you have a limit of water that you can add from the trim water that you took away, right? So if you took away, let's say, a gallon, 2 gallons per cubic yard, you have 20 gallons in a 10 cubic yard truck that you can add. The owner may say, hey, I'm going to allow putting 10 gallons back, but don't put more than that. Any additions need to be coming from a high range, just for staying safe, given the lack of certainty in concrete production. It's not a perfect thing. So.
And based on your experience, what is the optimum slump for ease of placement?
Do you guys want to answer that one? Yeah, this is the thing, right?
Yes.
It depends, right? Workability depends. This is optimum. Optimum for what, right? That's why people don't understand sometimes what workability means and they confuse it with slump. Let's bring a simple example. If you need a slip form concrete, what is the optimum slump? 1 or 2,
Yeah.
maybe.
Because we said compacted.
Okay, let me go to the next one. Right? If you need a heavily congested rebar area and you need to place concrete, what typically will be? Maybe 6 to 8. So what is the right number? What is the right number to use? Who knows? What is application? What are your demands? What are your obstructions? That's your optimal number. The one that is going to allow you to place the concrete and provide proper consolidation so you can have the final product that you want. There's not a magic number, and that's where I believe even ACI needs to stay away from that. We at ACI cannot be calling for numbers that we don't know. Have the contractor, designer, producer determine what is right. We don't have anything to do in that game unless we know what we're dealing with.
I had a question about structural performance. So let's say you have a condition like you've got there. Obviously there can be some environmental concerns in terms of long-term performance or degradation. But what about structural performance if you get cracking like that?
You know, I'm not a structural engineer. I'm a civil engineer with my materials and construction experience. But typically, I will tell you what the structural engineer tells you is I'm not concerned with the structural performance. That goes only all the way to the cover. What my concern is durability. So what I've heard in most cases is I'm concerned about the durability because now you provide an easy access for corrosion and other, contamination. But typically it's covered. So unless you have an element that is actually going to use that cover, in the whole composite action, they will be concerned. But I tell you, one of the photos I show you there is for a project that, one of the photos I show you there that we had to remove the whole deck was for one of our projects in the northwest side that is a unique type of bridge that is not built all the time. And I would have expected that they were concerned about that. And they say, well, no, the reason why we're removing it is just because of the durability. We have enough composite action and post tension and rebar, and the concrete strength is going to be enough that we don't care about the cover. But the concern was durability at the end.